Hello everyone. Our next topic is equivalent circuit with respect to impedance point of view. Okay, in that first one is series circuit. The elements are said to be connected in series. If same current is flowing through all the elements, then the circuit is called series circuit. Okay, so same current is flowing through all the elements, then the circuit is called series circuit. Consider the following circuits. Okay, here two elements are connected in series. So this is impedance 1 and this is impedance 2. Same current is flowing through both the impedances. Okay, so this current is flowing through this element and same current is flowing through this element. Okay, this across this impedance, the voltage drop is, let it be V1. So current is entering here, so it is plus and it is minus. So this is V1. The voltage across this impedance is, let it be V2. So current is enter here, it is plus and it is minus. The equivalent impedance is, this is Z equivalent. Z equivalent is equal to total voltage by total current, that is V by I. By KVL, so what is the KVL? This voltage. So here current is leaving from positive terminal, so it is minus. Current is entered positive terminal, so it is plus. Plus V1 plus V2 is equal to 0. So what is V? V is equal to V1 plus V2. Now, according to Ohm's law, what is V1? V equal to IR or IZ. So this is I into Z1. And what is V2? I into Z2. Now what is voltage? That is this expression from 1. Voltage V is equal to IZ1 plus IZ2. Take common I here. V is equal to I into Z1 plus Z2. So what is V by I? V by I is equal to Z1 plus Z2. So this is Z equivalent. Okay, if two elements are connected in series, the equivalent impedance is sum of two elements, that is Z1 plus Z2. Similarly, coming to this circuit, so what is equivalent? By KVL. So this is Z equivalent. Z equivalent is equal to total voltage by total current. So current is entering here. So this is positive, this is negative. Voltage across impedance 1 is V1. So voltage across V2 is, Z2 is V2. Similarly, voltage across impedance 3 is V3. So current is enter here, so it is positive. Again it is current is enter here, it is positive. By KVL, we will get V is equal to V1 plus V2 plus V3. So what is V1? V1 means IZ1 plus IZ2 plus IZ3. Take common here I. So V is equal to I into Z1 plus Z2 plus Z3. So what is Z equivalent now? Z equivalent is equal to V by I. Bring this current from this side to this side. You will get Z1 plus Z2 plus Z3. Okay. For suppose if n impedances are connected in series. Okay. This is n impedances are connected in series. So what is the Z equivalent? Z equivalent is equal to Z1 plus Z2 plus Z3 plus and so on Zn. Sum of all the impedances. Sum of all the impedances. For suppose if Z is equal to R, that is pure resistor. Impedance is pure resistor. So what is Z equivalent? R equivalent is equal to R1 plus R2 plus R3 plus and so on Rn. For suppose impedances are inductors, that means this is a pure inductor. For suppose this is a pure inductor and this is pure inductor, and this is pure inductor, and so on. If all these elements are inductors, so what is the equivalent, that is the impedance of inductance is Z is equal to j omega L. Impedance of inductance is j omega L. Here omega is the angular frequency, that is in radians per second, and L is the inductance of inductor, that is in Henry. Now from this expression, j omega into L equivalent is equal to j omega L1 plus j omega L2 plus j omega L3 and so on plus j omega Ln. If you take j omega common here, so what we get, and cancel from both sides, that is here j omega cancel, you will get L equivalent is equal to L1 plus L2 plus L3 plus and so on plus Ln. For suppose if elements are capacitors, so for capacitor impedance is Z is equal to 1 by j omega c. For capacitor impedance is 1 by j omega c. These are in ohms. Okay, this is ohms, this is ohms, this is ohms. Now from this expression Z equivalent, what we get, 1 by j omega c equivalent is equal to 1 by j omega c1 plus 1 by j omega c2 plus and so on plus 1 by j omega cn. From the right side take common j omega. So if you take common j omega, here j omega gets cancelled, so the remaining expression is c equivalent is equal to 1 by c1 plus 1 by c2 plus 1 by c3 and so on plus 1 by cn. Okay, if you observe here, if resistors are connected in series, the equivalent is sum of all resistors. If inductors are connected in series, the equivalent inductance is sum of all inductance. But if capacitors are connected in series, the inverse of equivalent capacitance is equal to sum of inverse of individual capacitances. Okay, for suppose if two capacitors are connected in series, consider only two capacitors, that means up to here. So what is the C equivalent? 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Okay, if you solve this, you will get C equivalent is equal to C1 C2 by C1 plus C2. If two capacitors are connected in series, you will get C1 C2 by C1 plus C2. Next one, voltage division rule. Okay, so if two impedances are connected in series, voltage is divided. Current is same, but voltage is divided. The total voltage is divided into two parts, that is V1 and V2. Now how to find out V1 and V2? So what is a V1? V1 is equal to I into Z1. And what is I? What is the Z equivalent? Z equivalent is equal to V by I, that is equal to Z1 plus Z2. From this, what is the current? I is equal to V by Z1 plus Z2. Substitute this current in this equation. So what is V1? V by Z1 plus Z2 into Z1. Now what is V1? V1 is equal to Z1 by Z1 plus Z2 into V. Okay, if you observe here, so the voltage across impedance 1 is Z1 by total impedance Z1 plus Z2 into total voltage. That means the voltage across V1, the voltage across impedance 1 is same impedance by total impedance. Same impedance by total impedance. For suppose Z is equal to resistor, that is Z equal to R. So total impedance is, that is voltage across R1 is R1 by total resistance R1 plus R2 into total voltage. Same impedance by, that is same resistance by total resistance into total voltage. For suppose if Z is equal to L, that means inductor. So what is V1? V1 is equal to same. For resistor and inductor, formulas are same, but if capacitor is given, formulas are differ. So this is L1 by same inductance by total inductance into total voltage. If it is capacitor, okay, so voltage across capacitor is opposite capacitance. So what is opposite capacitance? C2 by total capacitance C1 plus C2 into V. Okay, the derivation of this formula is, so what is V1? V1 is equal to IZ1. So what is the current from this? V by Z1 plus Z2. Impedance of capacitor is 1 by j omega C1 and Z2 is 1 by j omega C2. So from this, I is equal to V by 1 by j omega C1 plus 1 by j omega C2. Substitute this current and this impedance value in this equation. What is this equation? This equation. So V1 is equal to V by, or you can write V into 1 by, so take LCM here. This is j omega C1 into j omega C2 divided by j omega C1 plus j omega C2 into Z1 j1 by j omega C1. So here if you take common j omega, 1 j omega is cancelled and this j omega gets cancelled. C1 gets cancelled. So what is the remaining parameters? C2. Okay, this is C2 divided by C1 plus C2 into voltage, total voltage. Okay, so this is the opposite capacitance by total capacitance into total voltage. For suppose if 3 or more capacitors are connected in series, so what is the voltage division rule? That means what is the voltage across capacitor 1? V1 is equal to opposite capacitance. Opposite capacitance means consider equivalent of these two capacitors. Okay, this is C3. Equivalent of these two capacitors is C2 C3 by C2 plus C3. Okay, so equivalent of capacitors, that means C2 C3 by C2 plus C3 divided by total capacitance. So this is C1 plus C2 C3 by C2 plus C3 into total voltage. Okay, this is the formula. Opposite capacitance means consider equivalent of remaining capacitors. If 4 capacitors are connected in, consider equivalent of these 3 capacitors. So what is the equivalent of first? What is the voltage across first capacitor? Opposite capacitance or equivalent of other capacitors by total capacitance C1 plus equivalent of this capacitors into total voltage. So you will get what we get, C2 C3 by C1 C2 plus C2 C3 plus C3 C1 into total voltage. Okay, so whenever 3 or more capacitors are given, so remember this formula. Similarly, if 3 or more resistors are connected in series or 3 or more inductors are connected in series, for both the circuits you will get same values, that is voltage V1 is equal to same resistance R1 by total resistance. So what is the equivalent of other resistors? These are connected in series, so the equivalent of these two are R2 plus R3. So the total resistance is R1 plus R2 plus R3 into total voltage. If resistors or inductors are given, there is no problem with series circuit, that is voltage division rule. Now how to find V2, that is voltage across another resistor. The voltage across R2 means the voltage across R2 is V2 is equal to same resistance. So same resistance by, so what is the total resistance? See, the See here, R1 and R3 are connected in series. So the equivalent is R1 plus R3. Total resistance is R1 plus R2 plus R3 into total voltage. Similarly, V3, same resistance by total resistance into total voltage. But for capacitors, formula is different. Similarly, for inductors, for suppose these are inductors, so voltage across first inductor L1 is equal to same inductance by total inductance L1 plus L2 plus L3 into total voltage. Similarly, V2, same inductance L2 by L1 plus L2 plus L3 into total voltage. Similarly, third inductor, same inductor, that is L3 by total inductance L1 plus L2 plus L3 into total voltage. This is about the series circuit. In the next lecture, I will discuss parallel circuit. Okay, thank you for watching.